All right, so to continue our conversation from class today, I figured it would be worth it to just kind of walk through number 5 again. So we've got our ladder that's 25 feet long and we're leaning against the wall of a house. I'm just going to draw my sketch again here. Here's my house. There's my 25-foot ladder. And we said that this diagram is going to make a right triangle because we're concentrating on this area on the outside of the house. So the base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So we're saying that this part of the ladder is kind of sliding down the wall. So we're sliding down this way. And as we're sliding down that way, the base of our ladder is going that way. So we're saying that our ladder is moving outwards. We want to know how fast the top is moving down the wall when the base of the ladder is 24 feet from the wall. So we said as the base is moving outwards, we said that the top of the ladder is going to be sliding down the wall. So we know that this is going to be some sort of a rate here. All right, and the question is asking how fast are we moving when the base of the ladder is exactly 24 feet from the wall? So we're saying that this distance here is 24 feet. And we said that we would label these kind of as we would think about the XY coordinate plane. So I'm going to label this bottom distance as X, this kind of vertical distance as Y, and we said that we would call this diagonal distance Z. So we know a couple of other things, but we said that just using what we know about right triangles in the Pythagorean theorem, we are able to use the X squared plus Y squared is equal to Z squared to figure out what this Y value would be, which we will see is going to be important when we set up our equation. So our 24 squared plus our y squared is going to be equal to 25 squared. So that'll give us 576 plus y squared is going to be equal to 625, which should give us a y squared equal to 49, which is going to tell us that our vertical distance at the moment that the horizontal distance is 24 feet is going to be 7 feet. All right, so then we have to talk about rates. So we were kind of discussing the rate of change of this diagonal part at the end of class. We said that the rate of change over here of the ladder is going to be 0 because as this distance is changing and this distance is changing, the length of the ladder is not going to be changing at all. So the rate of change of the length of the ladder is going to be 0 since this length is not going to be changing. So we also know from just reading through the problem that the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So this distance, we're talking about the bottom side of the ladder being pulled away at a rate of 2 feet per second. So since we're calling this bottom distance X, I'm going to say the rate of change at which the X is changing, I'll call that dx dt, and we're going to call that 2. And we can use feet per second here. And I'm going to make that rate of change a positive rate of change because this length is increasing. As this bottom of the ladder is being kind of pulled out this way, this bottom length is increasing, which is going to make this rate positive. Okay, so then we need a formula that's going to relate all of this stuff. So we know we have an X, we know we have a Y, we know we have a Z, we have a rate of change of Z, which I'm going to actually call this dz dt, and we have a dx dt. What we're looking for is the rate of change at which the top of the ladder is sliding down the house. So what we are actually looking for is dy dt. We don't know what this rate of change is. That's what we want to know. All right, so what we can do is we can actually go back to the Pythagorean theorem. We've got a right triangle going on here. So what I'm going to actually write in terms of the formula that's going to relate all of these lengths is just going to be x squared plus y squared is equal to z squared. So when I take the derivative of this, that's going to be 2x times dx dt plus 2y times dy dt is going to be equal to 2z times dz dt. Because remember that we would need to get the derivative of each one of these variables with respect to time as well, using our chain rule. So then I'm going to fill in what I know. So I've got a 2. I'm going to multiply that by my x distance of 24. And I'm going to be multiplying that by the rate of change of x of 2. plus 2 times the y. We said that this vertical distance at the moment when the horizontal distance is 24 would be 7. And we're looking for what dy dt is. We want to know what the rate of change is as the ladder is slipping down the wall. So we don't know what dy dt is. And that's going to be equal to 2 times z. So we said that z was the length of the ladder, so 25. And dz dt is representing the rate of change of the ladder, which we said was 0 because the length of the ladder is not changing. So that's going to actually end up working pretty nicely over there. So I'm going to multiply this out. So 2 times 24 times 2 will give me 96, plus 2 times 7, 14 dy dt. And that is actually just going to be equal to 0 on the right-hand side. So then I want to know what dy dt is. So I'm going to move the 96. So 14 dy dt is going to be equal to negative 96. And then I can go ahead and divide. And I would want to simplify this as much as I can. So I believe that is negative 48 over 7. So in terms of the sign of this, we're noticing that the sign of dy dt is a negative, which makes sense because when our rates of change are decreasing, or when the length is getting shorter, your rate is actually going to be negative. So I'm just going to summarize that up here. So when your rate is increasing or when the length is getting longer, you should be ending up with something that is a positive rate of change. When you're decreasing in size or your length is getting shorter, your rate of change should be a negative. So that's kind of a good way to check to see if your ending value makes sense. So since as the ladder is sliding down the wall, this vertical distance is getting shorter. So that means that this rate of change would be negative. So in terms of actual units, we know that this is just a length that is changing. dy dt is representing a length. So our units on dy dt would be just in feet per second. So I can kind of summarize and say the top of the ladder is moving down the wall. I'm going to say at a rate of 48 over 7 feet per second. Notice that I'm not putting the negative there because I'm indicating that we're moving down the wall. And when we are moving down the wall, that is implying that that would be negative. So the top of the ladder is moving down the wall at a rate of 48 over 7 feet per second. All right. So let's talk about number 6. So a boat is being pulled in by means of a winch on a dock 12 feet above the deck of the boat. The winch pulls in the rope at a rate of 4 feet per second. Determine the speed of the boat when there is 13 feet of rope out. So what I'm looking for here is definitely a picture. So let's say that my boat is out on the water somewhere. And my dock, let's say, is right here. And I'm assuming that a winch means some sort of pulley. So I'm going to assume that there's something at the edge of the dock and my boat is going to be attached to that point on the dock by a rope. And it's telling us that the winch on the dock is 12 feet above the deck of the boat. So I'm going to kind of make myself a nice little diagram here. So we're talking about the deck of the boat. So we're just assuming that that's kind of that like horizontal line on our boat. The winch pulls the rope in at a rate of 4 feet per second. We want to determine the speed of the boat. All right. So this is telling us a couple of things. So this vertical distance, if we're talking about the distance above the deck of the boat, this vertical distance we're saying is 12. So I'm going to call this again, any vertical distance I generally call a y. And our units are feet. We also know that the winch pulls in the rope at a rate of 4 feet per second. So this rope, basically the boat is being pulled into the dock, and this rope right here that's attached to the boat as it's being pulled in is getting shorter. So this rate, we're saying, is getting pulled in at 4 feet per second. But kind of going off of what I just kind of wrote above in summary, since this distance or this length is getting shorter, I'm going to say that this is actually going to be a negative rate of change. And since this is representing kind of our diagonal, I'm actually going to call this dz dt. So our dz dt, or our rate of change of this diagonal distance, which I'm going to call z, with respect to time, would be -4. And again, it's negative because this distance is going to be getting shorter. So we want to determine the speed of the boat when there's 13 feet of rope out. So this is saying that at the instant where this length is 13, so I'm going to call that length z, I want to know what this rate is going to be. I want to know how fast the boat is moving inwards. So I want to know what is dx dt. And again, I'm calling this dx dt because I would call this kind of horizontal length my x value. So if it helps to kind of redraw, I'm going to redraw this because I drew it a little bit small over there. So we're talking about a right triangle. I know that I'm looking for the speed of the boat, so dx dt is what I'm looking for. I know that this is 12 feet. I know that this is 13 feet. And I know that the rate that this is changing is -4. So if we're thinking about kind of the same equation that we used above, we should be thinking about x squared, y squared, and z squared. So when you take the derivative, you should have information about x, dx dt, y, dy dt, and z and dz dt. So 2x dx dt plus 2y dy dt is going to be equal to 2z dz dt. And we have a bunch of this information already. We know that we're looking for dx dt. We know that we have this y value. We know that we've got the z and the dz dt. What we can go and figure out is this the x value here. So using what we know about the Pythagorean theorem, x squared plus y squared is equal to z squared, we can figure out what this last length is that we don't know yet. So x squared plus 12 squared is equal to 13 squared. So that should give me x squared, that's 144, that's 169. When you subtract those, I believe that's 25. So this missing length down at the bottom would be 5. All right, so as my boat is being pulled in, we know that this distance is getting shorter. This distance is also getting shorter. What we also need to think about is the dy dt. So we have two unknowns right now, a dx dt and a dy dt. But the nice thing is we actually know what the dy dt is, kind of similar to the last example when we said that the ladder wasn't changing length. This vertical distance is not going to be changing. So the distance from the deck of the boat up to the top of the dock, we're just going to be assuming it's not changing. I know it would probably change based on what like the tide was if we were talking about the ocean, but for purposes of this problem, we're going to say that dy dt is going to be 0 because this vertical distance, if the boat is being pulled in here, the deck of the boat is still going to be here, the top of the dock is still going to be here, so this distance is not going to be changing in relation to our other lengths that are changing. So then we can go ahead and plug what we know. So 2 times our x value of 5, we're looking for dx dt. That's what we're ultimately trying to find. Plus 2 times the y value of 12 times the dy dt of 0 is going to be equal to 2 times the z of 13 times the dz dt of -4. That's going to give me a 10 dx dt. And then over on the other side, it's going to give me a -104. And then when I go ahead and divide each side by 10, it's going to give me a dx dt of -52 over 5. And since this is a length that is changing, I want to know its units. So it looks like feet per second. So my speed of my boat when there is exactly 13 feet of rope out would be speed of the boat is negative 52 over 5 feet per second. I know it seems kind of weird to use the negative here, but remember that as our boat is being pulled in, that distance is getting shorter. So this definitely should be a negative unit of time. And when we talked about speed, when we were talking about like initially like the velocity problems, we want to take the absolute value of that. So I'm going to say the speed of the boat here is actually going to be 52 over 5 feet per second. So again, remember when you're talking speed, you always want to take the absolute value of your velocity. So positive 52 over 5 feet per second, but that is a negative because remember that that distance is getting shorter as you're moving the boat in. All right, so it is your turn to try some practice problems. Let me know if you have any questions on anything.